It lords over the solar system. A mega-world, 2.5 times the mass of all the other planets combined. This spinning giant whips up hazardous radiation, ferocious hurricanes, and treacherous magnetic fields. A spacecraft charges into the maelstrom, daring the planet Jupiter to give up its secrets. Juno is part of a larger effort to see into giant Jupiter, to glimpse a time over 4 billion years ago, when planets were born and obliterated, flung into space or tossed into the sun. It was a time when the fate of our own small and fragile world hung in the balance. The Greeks called him Zeus, the Romans Jupiter. The king of the gods hid his nefarious activities behind swirling clouds. Only his wife, the goddess Juno, could pierce the veil of mists to catch him in the act. NASA's Juno, the Jupiter near-polar orbiter, left Earth on a mission to peer into the mysterious Jovian atmosphere, to find clues to the powerful forces that churn beneath its roiling cloud tops. At some 300,000 times the mass of Earth, Jupiter holds over 70% of the mass of the solar system beyond the Sun. Juno is the latest in a series of missions designed to measure the properties of the planet, how it got so large, and how it shaped a rocky blue world, Earth. To understand Jupiter's early years, astronomers have been watching another solar system take shape. Out in the constellation Pictor, 63.4 light-years away, a young star, Beta Pictoris, is growing its first crop of planets. One is large enough and far enough from the star to be photographed. Beta Pictoris b. Astronomers have now seen it on both sides of its orbit. Look at Beta Pic and you'll see a snapshot of our solar system more than 4 billion years ago. The observed planet is growing within the outer zone, amid clouds of dust and gas, ice, and countless small objects called planetesimals. With matter swirling into it, the planet is likely a fury of gravitational and magnetic energy. Likewise, its distant cousin, Jupiter, is surrounded by a raging but invisible maelstrom. The king planet's magnetic field is 20,000 times stronger than that of Earth. Looking up from Earth, If you could see Jupiter's magnetosphere in the night sky, it would appear wider than the full moon. Jupiter's zone of magnetic influence is so large that it flares out beyond the orbit of Saturn, like a lightning bolt hurled by Zeus into the outer solar system. Jupiter's magnetic field is the product of a powerful double dynamo. One is down deep and permeates the planet. The other, close to the surface, rings the equator. When Jupiter's moon Io moves through this magnetic field, it emits powerful bursts of radio energy, strong enough to be detected on Earth. Volcanic eruptions on Io send a flood of charged particles into this field. They in turn energize massive auroras that light up the poles on this giant world. A haze of charged particles races around the planet, forming a belt of radiation 1,000 times the lethal dose for humans. Flying by in 1973, Pioneer 10 provided the first hints of this radiation belt when it passed within 130,000 kilometers of Jupiter's cloud tops. A year later, Pioneer 11 took the first close-ups of the Great Red Spot, Jupiter's immense signature storm. The Pioneer findings informed the design of the twin Voyager spacecraft. Launched in 1977, engineers shielded critical Voyager components from radiation. That allowed the Voyager craft to capture some 19,000 images, including new views of Jupiter's ghostly rings. The startling icy terrain of its big moons, Europa and Ganymede, and powerful active volcanoes on its inner moon, Io. The Galileo mission got even closer in 1995. Galileo sent back a treasure trove of discoveries about Jupiter's atmosphere. With a composition nearly identical to the Sun, Jupiter offers a window into the birth of our solar system some 5 billion years ago. Stars and planets are born when clouds of gas and dust contract, often quickened by the explosion of a nearby star. A shockwave from the dying star causes the cloud to collapse and to spin. As matter flows into its center, temperatures rise high enough to create a dim protostar. Within the disk, billions of tiny dust particles collide and stick together, forming sand-like grains called chondrules. Attracted to one another by gravity and static electricity, chondrules join to form pebbles. Pebbles become boulders, and finally, planetesimals. These kilometer-scale objects can collide, sticking together or breaking apart. Meanwhile, matter continues to flow into the central star. As the star brightens, winds of radiation begin to blow, pushing the remaining dust and gas outwards. At some distance out, called the ice line, temperatures in the nebula are low enough for water, methane, ammonia, and carbon compounds to form solid crystals. Out here, objects made of rock and ice come together quickly to form protoplanets. By this process, the largest grow the fastest. To withstand Jupiter's punishing radiation, Juno's electronic circuits were encased in a titanium vault. Its components were built of radiation-hardened material. Every part of Juno that can be is wrapped in lead foil. Launched on August 5, 2011, Juno is formally known as the Jupiter Near-Polar Explorer. It was the second launch of NASA's New Frontiers program. This series of medium-sized missions is designed to expand our knowledge of planetary bodies and deliver new insights into the origins of the solar system. The first mission, called New Horizons, traveled 9.5 years to the outer solar system. It mapped the surfaces of Pluto and its moon, Charon, collected information on their geology, and found clues to their complex and violent history. The third mission, called OSIRIS-REx, was sent out in 2016 to an asteroid called 101955 Bennu. The idea was to actually land on the asteroid, pick up rocks, and return them to Earth. These samples will help address basic questions not only about the birth of the solar system, but the origin of organic molecules that helped spark the evolution of life on Earth. To score important new science, these missions have each taken on daunting technical challenges. For Juno, the challenge is to fly close to Jupiter without getting fried by its powerful radiation belts. To do this, the spacecraft was sent into a series of highly elliptical orbits to track across Jupiter's poles, then to dive beneath its radiation belts and pass within 4,100 kilometers of Jupiter's cloud tops. Out of each 53-day orbit, Jupiter spends just 2 hours in the zone of maximum danger. The craft spins 3 times each minute, allowing its instruments to capture about 400 slices of data from pole to pole. Besides photographing its complex surface features, Juno is performing a CAT scan of Jupiter. When scientists look at the planet, they see structures like those in Earth's atmosphere. Cyclones, anticyclones, jet streams, storms pushing upward. And yet Jupiter and its weather systems are radically different. For one thing, the planet is much larger. It also rotates faster and sits much farther from the sun's warming radiation. The intricate structures scrolling across the cloud tops are a window to conditions deep inside it. Juno's data shows that Jupiter's surface flows extend down as deep as 3,000 kilometers. Below that, magnetic fields slow them way down and pull the planet into a uniform rotation. Deeper still, scientists suspect the inner zone is a sphere of metallic hydrogen surrounding a solid core of rock and ice. Throughout most of the 20th century, scientists theorized that giant planets like Jupiter form in long orbits far from their stars. While these planets grow by scooping up a rich supply of icy planetesimals. Planets inside the ice line stay small because there is less solid food during their formative years. This general understanding was blown away by recent exoplanet discoveries. The Kepler space missions, along with ground-based planet hunting systems, have identified more than 2,000 stars with orbiting worlds. So far, few resemble our solar system. The inner orbits of many star systems are graced with so-called hot Jupiters, large gas giants the size of Jupiter or larger that whip around their parent stars at close range. Some are being stripped of gas by powerful solar winds. Then there's a class of rocky super-Earths. At about twice the mass of our home planet, they occupy the innermost orbits of many other solar systems. It turns out that the most common planets within these inner regions are not rocky at all. It's a class of gas dwarfs, smaller than our Neptune, that weigh up to about 10 Earth masses. Smaller, Earth-sized planets are in fact rare. How did our solar system evolve in such a different direction? The answer may lie in Jupiter's turbulent past. As Juno passes in close to the planet, her path bends in response to concentrations of mass beneath its surface. Because Jupiter isn't solid, those regions are free to move and shift. Jupiter spins faster than any other planet in the solar system, turning once every 9 hours and 55 minutes. That bulges its equator out and flattens its poles. By plotting tiny variations in Juno's timing as it orbits, investigators can detect concentrations of mass below the surface. What Jupiter is made of, how its density varies, how forcefully it now spins, and how massive or solid is its core. These are all clues as to when and how it formed. Our solar system is still buzzing with the remnants of its birth. Wandering rocks that haven't changed since they formed almost 5 billion years ago. Most are so small that when they encounter Earth, they simply burn up in the atmosphere. A few larger ones survived the fall. Scientists date these planetary shards by measuring molecular variations, called isotopes, of two particular metals, tungsten and molybdenum. These meteorites appear to come from two separate populations that formed in the inner and the outer solar system. Something must have driven a wedge between these two regions, preventing them from mixing. If this great divider was the young Jupiter, it had to have grown very fast, reaching about 20 times the mass of Earth within the first million years of the Sun's formation. Its gas giant neighbors, Saturn, Uranus, and Neptune, would have formed in its wake. By dividing the solar system in this way, Jupiter would have cut off the flow of matter into the inner solar system, stalling the formation of large rocky planets, or super-Earths. Then came one of the most impactful events in the history of our solar system. One set in motion by Jupiter's sensational rise. The discovery of large gas planets within the inner regions of other solar systems has prompted a whole new set of questions. If these giant planets formed beyond the ice line, then migrated inward, could Jupiter have followed a similar path? To test this idea, scientists used a supercomputer to reproduce the early evolution of our solar system. They plugged a set of initial conditions into a program designed to simulate the interaction of gas and dust, gravity and energy. The simulation takes us into one cold and dusty corner of the galaxy 5 billion years ago. Shockwaves from a supernova explosion perturbed the cloud, causing it to collapse into a dense central region. Near its center is a vast rotating hurricane of dust, gas, and water. In its eye, matter flows into a newborn star along a thin disk. Flashes of light within the disk represent collisions among larger objects. Concentric rings show their orbits. The large orbit on the periphery is Jupiter, the first full-sized planet to form. From its position far from the Sun, it has scooped up huge amounts of ice and hydrogen gas. Within 1 million years of its birth, Jupiter responds to the gravity of the Sun and the mass of the inner solar system. The model shows Jupiter's inward spiral, known as the Grand Tack. As the giant planet's orbit shrinks, it sends the inner solar system into chaos. Jupiter flings most large objects into looping orbits around the outer solar system or streaming into the Sun. Finally, Jupiter feels the pull of another growing planet, Saturn, and retreats to the outer solar system. Jupiter gradually settled back into its current position. That left some 20 or 30 small planetary embryos to patrol the inner solar system. Here, the simulation speeds up to cover the next 50 million years. As these embryos tug on one another, their orbits destabilize. When the dust finally settles, perhaps 100 million years later, the number of planets is down to 5, including Earth and a Mars-sized world, Theia. Everything changed when Earth and Theia crossed paths. A computer model gives us a view of the first 24 hours. Theia shears about 1/3 of Earth away. Its shattered remains envelop Earth in a shockwave of superheated, vaporized rock. A molten ring forms around the planet, subjecting Earth to a rain of secondary impacts. Within only a century, this orbiting ring will cool and coalesce into a single orbiting body. The Moon. The violence of the Moon's formation would have left Earth spinning rapidly on a slightly tilted axis. A day lasted only about 5 hours. In time, the Moon stabilized the planet's tilt, holding it steady. As it moved out to its current distance from Earth, it gradually slowed our planet's spin. If the grand tack theory explains the evolution of the inner solar system, then it may explain a host of details that have long puzzled scientists. Why, for example, is Mars so small? The idea is that Jupiter swept up much of the dust that accumulated just inside the ice line, starving Mars. What explains differences among the various classes of asteroids? The asteroid Bennu, at roughly 500 meters in diameter, appears to be a fossil from the time Jupiter sailed toward the Sun. This dark object is made up of carbon-rich clay materials, born in the explosion of dying stars. Bennu itself is a product of collisions. In its 4 billion years of travel, the asteroid has likely been stretched, pulled apart, and reformed. To trace the asteroid's origins, scientists have launched the OSIRIS-REx mission, with the goal of returning a sample to labs back on Earth. They plan to send another mission, called Lucy, to an ensemble of asteroids that trails Jupiter. These so-called Trojan asteroids take their name from soldiers who hid inside the giant horse in Homer's Iliad. The thinking is that Jupiter began pulling them along within the first million years of its history. Then there's the main asteroid belt, a vast hoop of rocks between Mars and Jupiter. Scientists believe that as Jupiter moved toward the Sun during the Grand Tack, it dispersed an original ring of rocks and dust. When Jupiter moved back out, it drew a whole new collection of rocks back in. By studying the composition of these asteroids, including a dwarf planet called Ceres, scientists hope to confirm their origin. Finally, the giant planet carries its own artifacts from the early solar system. Most of its 79 moons are asteroids or comets captured over the years when they flew too close to the giant planet. The 4 largest satellites are different. If Io, Europa, Ganymede or Callisto orbited the Sun, we call them dwarf planets. Scientists believe these moons formed slowly from a disk of ice and debris that circled Jupiter very late in its formation. All 4 are in tidal lock. Like our own moon, each keeps the same face toward Jupiter. Io, the volcano moon, orbits closest to Jupiter. Io shows what can come from living too close to an unsympathetic god. Heaved and stretched by gravitational interactions with Jupiter, and warped by tidal resonances with the other 3 large moons. Io is constantly being turned inside out. With hundreds of volcanoes, some blasting lava to altitudes up to 400 kilometers, Io is the most geologically active body in the solar system. Next is Europa, with its bright, young, glossy surface covered in ice. Ganymede, with a diameter of 5,268 kilometers, is the largest moon in the solar system, larger even than the planet Mercury. Then there's Callisto, 2 million kilometers from Jupiter. Spacecraft sensors have shown that these 3 icy moons, Europa, Callisto, and Ganymede, hold different amounts of water beneath their surfaces. In Jupiter's early years, ice, dust, and gas flowed into the planet along a disk. The Grand Tack model predicts that Jupiter's disk would have shrunk as the planet moved toward the Sun. The 2 larger ice moons must have started forming before that. Europa formed later and had less water around it to attract, and Io had almost none. Jupiter's major moons didn't hoard all of the planet's icy bounty. On its inward journey, Jupiter would have carried a wave of ice in its wake, delivering water that might, one day, have filled Earth's oceans. Once settled back in the outer solar system, Jupiter, along with Saturn, began to hurl still more icy material to the inner solar system. Shards of rock and ice rain down on Mars, Earth, Venus, Mercury, and the Moon. The lunar landscape today bears witness to this period. A 300 million year fusillade known as the Late Heavy Bombardment. Based on data from the Moon, scientists estimate that our planet would have been hit by at least 4 objects 5,000 kilometers across. Each capable of turning Earth's entire surface to molten lava. These collisions may have unleashed a process critical to the emergence of life, called impact erosion. The impacts blasted hot radioactive metals like uranium and potassium off the planet. That allowed the planet's outer crust to rapidly cool and water to remain. Scientists believed that Earth was a water planet in its early years. Zipping along at 200,000 kilometers per hour, the Juno spacecraft takes 2 hours to pass from pole to pole. In that time, it records a variety of readings of a world that remains a gargantuan work in progress. Winds up to 650 kilometers per hour whip cold clouds of methane, hydrogen sulfide, water, and other compounds into endlessly swirling works of art. Sometimes white clouds of ammonia snow fly over the wide southern red band, making it seem to disappear from Earth's point of view. It's cold in the clouds, about minus 125 degrees Celsius. Deep within the atmosphere, showers of compressed carbon may fall between the layers in a diamond rain. White spots mark the crests of enormous waves rising and falling along the surface. Twirling storms explode into the upper atmosphere, propelled by heating hundreds of kilometers below. They unleash lightning bolts far larger and stronger than any seen on Earth. It's the polar regions, photographed for the first time ever by Juno, that have defied expectations. Here, the belts and zones of the middle latitudes disappear, and the atmosphere is dominated by an ensemble of hurricanes. During its 4th pass over the planet, Juno's infrared imaging instrument captured these structures in 3 dimensions. The northern pole hosts a giant cyclone surrounded by 8 smaller ones, each over 4,000 kilometers wide. The bright yellow colors show deeper, warmer areas. The darker red colors are cooler cloud tops. They likely arise from the interaction of smooth horizontal flows in low latitudes and turbulence at the poles. The spin of the planet causes them to drift poleward. This raw sequence gives a sense of their spinning movements. By contrast, the southern cyclone is surrounded by 5 cyclones. From an Earth perspective, even these smaller ones are vast, up to 7,000 kilometers in diameter, or about the width of Mars. Why these structures persist without merging is not known. If there's a single feature on Jupiter that has held us in its thrall, it's the Great Red Spot. Juno has been flying directly over it at an altitude of 9,000 kilometers, close enough to see fine details. Historical records show this huge high-pressure zone is at least 350 years old. Astronomers have been measuring it since 1830. At about 16,500 kilometers across, it's 10 times larger than Earth's largest typhoons. Juno's data suggests the Great Red Spot heats the planet's upper atmosphere. The big cyclone rotates counterclockwise once every 6 Earth days. That period has been getting shorter as the storm tightens. The color sometimes fades for years, then intensifies. No one knows why. It was the bright light of Jupiter that attracted Galileo Galilei in January of 1610. His small telescope was powerful enough to resolve the 4 large moons circling the Great Orb. If another world could have satellites, he reasoned, it seemed possible that Earth could be a satellite of the Sun. If only we could go back in time to show Galileo close-ups of Jupiter captured by Juno. How amazed he'd be to learn that such giant planets are common in solar systems throughout the galaxy. That billions of years ago, it marauded through our own infant solar system. Destroying worlds, setting the stage for new ones. What would he say of our news that Jupiter left in its wake a quiet zone, where a world with oceans on its surface would form and over time give rise to life?